Hey everybody, John Shutsky here, and I am going to be talking here today about designing for safety. So this is the first video of a three-part safety series, Designing for Safety. I'm going to be talking about the engineer's responsibility in safety and risk management as is defined by the Engineering Code of Ethics. And I will also in this video be introducing an important concept, a fundamental concept in safety engineering called the safety hierarchy. In video number 2, I will be talking about risk assessment, actually putting some numbers to risk, setting priorities, and actually applying a technique that we call failure modes and effects analysis, or you may sometimes see this referred to as FMEA, failure modes and effects analysis. In part 3, or video number 3, I will be talking about human factors. As human beings, we have all kinds of limitations. Those include physical limitations like strength, reaction time, our ability to physically maneuver around the work that we do or the products that we work with. But I'll also talk a little bit about cognitive limitations. Those are things related to our decision-making ability, how we process information, and that human being is really critical. They're a really important part of assessing, controlling for risk. People are a key part of the equation. And these limitations of people are why what I'll talk about with the safety hierarchy in this particular video are so important and why engineers really do hold that ultimate responsibility. I'll also mention that these videos are required for a class that I teach, BSE 508, which I've just abbreviated here as Engineering Design. This is our 2-course capstone design sequence. And if you are a person who is not a practicing engineer or you'd like to learn more about this content or other things either connected to the course or to safety, I would encourage you to get in touch with me with the information that's provided below the video. So my objectives here today, and I've already alluded to these, I will be talking about the engineer's responsibilities relative to the Engineering Code of Ethics, really critical and super important for you to know, both in terms of being a practicing engineer, also for things like the FE exam. For those of you who are going to become licensed as a professional engineer, this code of ethics is really critical. Also talk about some of the implications if you choose not to follow the engineering code of ethics or you choose to not take seriously this issue of safety and risk management. It obviously has all kinds of implications. So I'll talk a little bit about those. And then again, I've mentioned this, I'll be talking about this critical framework, the safety hierarchy, in the last part of my presentation. Let me first of all begin by saying we live in a risk-filled world. There is not a day that goes by. If you read the news on your phone or you pick up a newspaper, there are so many things that happen in our world. There are things that happen locally. There are things that happen globally. Obviously, when we think about safety, many of us probably think about issues connected to injuries or what I will call trauma. That's traumatic injury. I prefer not to use the term accidents, and I'll talk more about that in a few minutes. We also need to talk about disease and illness. There's tons of it, as you know, and we've just gone through, or we're in the midst of hopefully wrapping up a global pandemic, something that engineers have actually played a little bit of a role in, actually a significant role, along with public health professionals and policymakers and biologists and other people. But engineers do have to be thinking about these things. Property damage and loss, we do see things all the time like fires and floods and natural disasters and tornadoes. Economic loss is a big part of that. Again, thinking back to 2020 and 2021, obviously there's been tremendous loss of life. There's been pain and suffering, but the economic impact has been just massive. As we've seen recently with government programs to come in and step in and backfill or provide support, largely to offset some of those huge economic losses that have occurred. And it's the same when we talk about injuries and other types of non-disease loss as well. And then the big thing is also long-term lost future opportunity. I oftentimes think about the work that I do in agriculture when we have a young person, for example, who is killed or injured seriously on a farm or another type of workplace. That long-term loss is really almost immeasurable. And again, when you think about things like the pandemic that has occurred, that long-term human potential across the planet is something that we'll never, ever be able to replace. Now, I do want to emphasize, and I've already done this a little bit as I've talked about things other than just injuries. We have to think about this as an issue that cuts across all domains of engineering. Too often, I hear my students say, like, well, I'm not a machinery systems undergraduate, or I'm not in a machinery systems program, so this doesn't really apply to me. Well, I'll have to say it does. And I'll give you some examples. Obviously, when we talk about machinery systems, we've got the potential for injury from the direct contact with hazardous forms of energy, kinetic energy in particular, or electrical energy. We also know that there are tremendous financial losses. So this is not just injuries. It's also when we have a large machine or another type of mechanical system, whether that's a factory machine or a farm machine, or even your car. If I'm driving a car and suddenly have a breakdown and I'm having to get to and from school or to work, there's significant downtime losses where you have to go get something repaired. It's out of commission. You may be hampered from doing the work that you do. So those financial costs can be really significant. We also have the potential for liability loss, and I'll come back and talk more about this. Engineers are subject to the potential for being sued as a result of either negligence or some other type of taking a court or an attorney or a plaintiff taking a civil action against an engineer or their company. That's something that can be quite critical, particularly if something is poorly designed and if people don't pay attention to these notions or these ideas that we're talking about. What about environmental systems and natural resources? Well, there are all kinds of hazards that we need to be thinking about and evaluating and controlling for. Obviously, we have the potential for human risk. That includes things like floods and other types of drownings. We have had on occasion young children who have drowned as a result of designed either ponds on farms or wetlands, and I actually talk about that in a future video. And then there's also the potential risk for contaminants, groundwater contaminants, surface water contaminants, air contaminants. So we really do worry about those kinds of things when we talk about energy production, whether that's at the farm level or a larger scale, either publicly or privately owned energy producer. Financial loss, the potential for failed design if something is not appropriately designed. I think about the catastrophic failure of the systems up near the Wisconsin Dells when Lake Delton and the structures surrounding it failed back in 2008 because of heavy rainfalls. And the losses to the community, the losses to individual property owners, all of those are really, really significant in the millions or even billions of dollars. We also know that there are potential risks to wildlife, to our climate. So we need to think about the risk associated with how is our design going to affect the climate? Is it going to affect the carbon balance? How is it going to affect biodiversity in terms of risk to either wildlife or just the biodiversity within that environment? And then finally, when we talk about food, bioprocess engineering, we need to think about, with food in particular, we need to think about foodborne illness. Foodborne illness is super important and a big concern of engineers who are working in the industry. We also need to think about the toxic impacts and toxicity impacts of the processes, the chemicals that we're using, the other types of manufacturing processes. And then finally, when we're talking about food and energy production, as is the case with any type of industry, we need to think about the waste streams that are coming or leaving a facility. We also need to think about the safety of products coming in. So there are all kinds of different risk and safety related considerations. I want to just talk a little bit about the specific work that I do on a daily basis. I think a lot of you probably know I'm a farm health and safety specialist. And the reason I spend so much time working on these issues is that agriculture is a particularly deadly industry. In fact, if you look at farming and ranching, it is our country's most dangerous occupation, as is measured by the fatality rate. A fatality rate or a death rate that's about 7 times higher than all other industries combined. We also know that in the state of Wisconsin, we're not immune from this issue. Just in Wisconsin, we've typically documented on the order of about 30 workplace deaths per year. That includes workplace, the farm, but also surrounding locations like people colliding with a farm machine being operated on a public highway. We just recently summarized some data from 2017 and 2018 that found that our numbers are even a little bit higher than what we expected. We also know that in a place like Wisconsin and also Minnesota, the Dakotas, Nebraska, we worked on some studies back in the 1990s, and we learned that about 20% of our farms, or roughly 1 in 5, will have a workplace injury here in this particular year. If you look at that in terms of the state of Wisconsin, just as an example, the number would be about 12,000. We have 60,000 farms, 1 in 5 will experience an injury, 12,000 injuries annually, and about 80% of those require some type of professional medical care or treatment. And then finally, people who work in farming, people who work in agriculture, experience an unusually high rate and a high level of exposure to a range of different unusual health hazards. So that includes gases from different products, from silage, from manure. We also are exposed to ultraviolet light because of outside working conditions, from sunlight, which increases the risk for skin cancer and other types of problems. We also have a lot of noise, a lot of vibration, and we have exposure to organic dust. So impacts to our lungs, other parts of our body, our critical organs are all potentially affected by the agricultural workplace. So obviously we've established that there are a lot of issues out there we need to pay attention to. And the question then really becomes, what about the role of the engineer? Now, one really critical concept that I want to introduce to you here is that almost all accidents, and I do use that term in quotes, all accidents are caused by exposure to a hazard, often accompanied by a transfer of energy. Now, kinetic energy is the most common. We also have stored energy, potential energy, electrical energy. We have energy in multiple forms, even chemical energy to some extent, heat energy, another common one. And I think, as most of you probably know, when you study physics and when you study the basic fundamentals of engineering, energy is a key part of that. That's why we have you take classes in heat transfer and thermodynamics, because energy and the control of energy is central to the role of engineers. I don't have time to go into a lot of detail about that, but it's energy conveyed or transferred at the wrong rate, at the wrong time, or in the wrong place. If a human being happens to be in a place where energy is being released, that the outcome is likely to be a serious or even a death-causing injury. And what I really want to nail home is, if I look at the term accident in Webster's dictionary, or if I look it up on the web, accident is often defined as something that happens as a result of chance. You know, it was just a bad roll of the dice, or fate, or luck. Or some people have even referred to accidents as being something that happened because of an act of God. And I tend to look at things a lot differently than that. And injuries are controllable. The vast majority of injuries can be prevented by the harnessing or the proper control of energy, or isolating people from energy sources. And that really does put engineers front and center. It puts us front and center through a framework that I'll come back to later called the safety hierarchy. The safety hierarchy really does dictate that design solutions are the preferred way of dealing with these potential hazards from kinetic and other forms of energy. And this is largely dictated, again, through the Engineering Code of Ethics. As a result, engineers are held to very, very high standards. Now, you may look at this picture and say, okay, what does that have to do with the race car, the racetrack here? This is the Indianapolis 500. This is actually a picture from 1987, the Indianapolis 500, that I'm sure a lot of you has run right around the time of Memorial Day in the month of May. And back in 1987, we had a young guy, I think he was in his early 40s or possibly late 30s. His name was Lyle Kurtenbach. Mr. Kurtenbach was from Wisconsin, actually, and happened to be at the Indy race, the Indianapolis 500. He was sitting between the third and the fourth turn. Back in 1987, these cars were racing around the track at probably a speed, I'm guessing in 1987, the top speed was probably around 205 to 210 miles per hour, 205 miles per hour. As these cars came around the track between the third turn and the fourth turn, one of the drivers had a wheel come off. That wheel obviously is, traveling at a high rate of speed along with the car. It ricocheted off of the car behind the driver that lost the wheel, and that wheel went up into the stands. By the time it hit Mr. Kurtenbach, who was probably sitting about 100 feet up off of the top of the track and back, by the time it hit him, it was probably traveling at a speed of well over 100 miles per hour. You've got air resistance that's going to slow that wheel down. But traveling at a high rate of speed, if you look online, they estimate that this wheel probably weighed about 25 pounds. I actually think it was probably a little bit heavier than that. But the bottom line is it hit Mr. Kurtenbach and it killed him probably instantly. Now, we talk about accidents being something that happened because of luck, chance, fate, something that you would have never expected, something that happened as a result of an act of God, if you will. From Mr. Kurtenbach's perspective, we could probably say, yeah, that definition, from his perspective, this was a really tragic accident. It's so unfortunate. He made his way down to Indianapolis. It's hard to get tickets. There's crowds. It's loud. It's noisy. It's just something, it's a kind of a once-in-a-lifetime type of an opportunity. And here he is sitting or standing there, and suddenly he is killed instantly as a result of this flying wheel. From his perspective, it was an accident. From the perspective of the Indianapolis 500, was it preventable? I guess I'll let you make the decision. I will say that since that time, they have installed a number of safeguards. They have installed a number of devices to prevent these kinds of things from happening. There have been a lot of questions about why that wheel came off of the driver's car. I would argue that from the perspective of the track, the engineers, the people who designed the facility, it in fact was preventable, and I would prefer we not call those kinds of events accidents. So let's talk a little bit. I've teased this a little bit. I've hinted at this. I want to talk about the Engineering Code of Ethics. The Engineering Code of Ethics, as I mentioned, when you take the FE exam as an engineer, or when you go on to get your PE, you will be expected to know the Engineering Code of Ethics. If you are interested, I actually have a similar video series that I do for my other class, Career Management for Engineers, a 3-part series on engineering ethics and a couple of good case studies. So you're going to get more detail if you're in that class as well. There's something called the Preamble. That's kind of the introduction to the safety hierarchy. And it says engineers, and I've shortened this a little bit. It actually says engineering has a direct and vital impact on the quality of life for all people. Accordingly, the services provided by engineers require, and then there's a long list of things, honesty and several other factors. And then the last phrase in that preamble is, and engineers must be dedicated to the protection of public health, safety, and welfare. So there it is, spelled out right in that very introduction paragraph, probably the most important part of the Engineering Code of Ethics, as is spelled out in that preamble. There are also a number of things that are called fundamental canons. Now, we're not talking about a canon like something that like a firearm cannon. We're talking, it's different spelling. A canon is like a central tenet, a central idea, almost a commandment, because these are essentially required. One of the fundamental canons is that engineers, in the fulfillment of their professional duties, shall hold paramount the safety, health, and welfare of the public. So there it is, right at the very beginning of these fundamental canons and at the preamble to the Engineering Code of Ethics. Engineers are the ones held responsible. So what are the consequences if I choose to ignore this, if I choose not to pay attention to my role, to learn about safety, to learn about human factors, to learn about and actually practice good risk assessment and control? What can happen? I can lose my customers. Obviously, a customer who was killed or injured by your product isn't going to be using or repurchasing your product in the future. But you also have this larger issue if you develop a bad reputation because of the sale or the manufacturing or the design of an unsafe product or a system. Again, this can be a machine, but this can also be an environmental feature that you're designing. If you develop this reputation that you're designing things unsafely, you will lose customers and you will lose your market. You also have the potential to suffer large economic consequences. This includes lawsuits that I talked about earlier. You could be the defendant in a lawsuit, defending yourself from a plaintiff who brings action against you. Oftentimes these are lawsuits for financial damages. And what ends up happening is if you are found or if a jury and judge rule against you because of your role as an engineer, that you did not take the proper precautions, you were maybe viewed as being negligent, or you put out a faulty product, you failed to warn somebody, you can have large multi-million dollar lawsuits in the form of either compensatory and or punitive damages. Compensatory damages, I'm compensating for their loss, either their direct loss or their indirect loss. That can include pain and suffering, by the way. And then punitive damages, if I am an engineer and I have willfully ignored my roles and responsibilities, I can be punished. Punitive means a punishing action. And those losses also can run in the hundreds of thousands or millions of dollars. And I've seen these happen in my career in a number of different cases and times. I've also served as an expert witness, and I've seen this sort of thing happen. And that's been my primary role. I've never actually been subject to something like this personally, but I have served as an expert witness, and I've seen people lose hundreds of thousands and millions of dollars as a result of damages. Another thing that can happen is if I'm repeatedly, willfully violating the engineering code of ethics, I'm not paying attention to my ethical responsibilities as an engineer, I can be subject to criminal prosecution. And then the last thing is probably the most important and the most common, and that's just the loss of trust and reputation. Now, I want you to just think about this a little bit. If you're a student in engineering, whether you're an undergraduate or a graduate student, you have had to work a long time to build your credentials, to build your skills, to build trust, to have professors and ultimately an employer, whether that's a company or an agency, put their trust in you. It's taken you years to build that. It will probably take you 5 to 10 years once you have left school to work for that company and really fully build your portfolio of experience so that you have the full trust that a company or agency is going to want to put into you. But guess what? Even though it might take you 5 to 10 years to build that trust, you can lose it overnight through a poor decision, again, through not adhering to some of these concepts that we're talking about. So let's finalize things here, or let's finish things up by talking about the safety hierarchy. We've got this professional engineering code of ethics, and then people say, well, okay, what does that mean? What do I need to do? And video number 2 will go into that whole notion of risk assessment. But the safety hierarchy is really like where the rubber hits the road, so to speak. The safety hierarchy, extremely critical idea. It is very, very consistent with the code of ethics that says engineers ultimately have that responsibility. The safety hierarchy also indirectly points to the fact that as human beings, we have significant limitations, and therefore we need to take that risk control responsibility out of the hands of users and consumers, and we need to put it back into, or we need to build it back into the design as engineers. It is not a rule or law, but it is embedded into standards, into some rules and laws. It's not directly stated, but it's embedded in terms of the spirit, the principles. It's also used commonly in legal arguments and civil lawsuits, as I've talked about, in terms of negligence and other responsibilities that an engineer has. And the last thing that I'll say before I show it to you is that ideally there is no one single solution. When I show you the safety hierarchy, we need to be thinking about multiple strategies on that hierarchy, even though there are some strategies that we know are going to probably be more effective than others. So here's the safety hierarchy. Here is what it looks like. And I do want to just give some credit to, you'll see it down at the bottom of this slide. There was a person who I knew quite well in the 1980s and 1990s. His name was Professor Ralph Barnett. Dr. Barnett taught engineering and risk management at a university, a technical institute actually in Illinois. And he ran a company in Chicago, actually a suburb of Chicago. The company's called Triadyne. And I will link to some of the Triadyne materials, including his rather famous paper called The Safety Hierarchy. There are other versions of this, by the way. If you search engineering design, safety hierarchy, and NIOSH, National Institute for Occupational Safety and Health, and also their parent organization, the Centers for Disease Control, they also have had they've done a lot of work and they've paid a lot of attention to a very similar hierarchy. Wording is a little bit different. The structure of the hierarchy is slightly different, but it has exactly these same principles embedded in it. And again, if you're in my class, these will be linked in the class module. So the safety hierarchy says this. It says that there are preferred ways. Those are the topmost ways of this upside down pyramid for dealing with safety. And by the way, safety and health problems, right? So this is not just injuries. This is also diseases. This also includes the pandemic from 2020 and 2021. It is far better. It is far more preferable. It is going to be far more effective, or you're going to have far greater impact if you find ways to eliminate hazards altogether. If you can find ways to design them out of your system so that they never exist and we never need to worry about the limitations and the abilities of people. I'll give you an example in a moment. Number 2 on the safety hierarchy, if that's not possible, then we really need to think about safeguarding devices. So this is things like guards and shields and interlock systems. So an example, if you have a washing machine, when I turn that washing machine on, you've got a large drum that potentially for a young child that puts their hand in a rotating washing machine drum, it can cause massive damage. It can probably cause amputations during the spin cycle. That's why we have an interlock, so that once that washing machine starts its cycle, we have a safeguarding device so that you cannot open up that washing machine until all moving parts have come to a standstill. Number 3 on the safety hierarchy is warnings. Now, warnings are critical. If you are an engineer, you must warn people about the hazards that exist or about their responsibilities with respect to safeguarding devices. For example, you need to tell a farmer, do not remove a power takeoff shield except for providing maintenance. And when you do, you must put it back on, right? So safety decals and signs and warnings, they're so prevalent. I don't know if any of you have ever recently operated a new chainsaw. When you buy the chainsaw, the packaging is full of warnings. Caution, danger, warning, all kinds of information. You look at the operator's manual. It is full of information. It's one of the reasons why a lot of products, even though you might be able to locate the operator's manual online, you actually are provided a physical copy of the manual. And the part that you're probably most often provided is the safety and warning information, right? Even with computer products, you have lots of warnings and precautions. The one problem is, as many of you know, you may have these manuals, you may have warnings on the product, on the packaging. Sometimes we choose not to pay attention. We may not read them. We may not have the time. We also may be looking at warnings that are in a language different than what we speak. And so as a result, warnings are important. Failure to warn is a central argument when an engineer gets sued. If they fail to warn, they're oftentimes going to lose an argument. They're going to lose in a civil lawsuit. So warning is crucial. However, it is number 3 on the safety hierarchy. Why? Because you're far better off eliminating that hazard or safeguarding so that that warning never really quite needs to exist, especially if you go to that topmost tier of the safety hierarchy, eliminating those hazards altogether. So warnings are important, but warnings have limited utility. Number 4 is training. So providing information about how to work with a product, how to work with an environmental system. If I'm putting out a piece of equipment for food manufacturing, I'm probably going to do a fair amount of training on how to appropriately use that piece of equipment. But that training is far less effective than if you are able to design safety into that equipment. It's required, it's necessary, but by itself is not adequate. And the same goes for personal protective equipment. I mean, if you think about the pandemic in 2020 and 2021, at first, there was a lot of hesitancy to recommend face coverings. If you remember back to Early 2020, March, April, people were really they were really uncertain. And part of the reason for that is we didn't know how effective personal protective equipment was going to be. We also knew that there was a shortage of appropriate personal protective equipment. So there was a lot of debate about cloth face coverings and other mechanisms. The reason why personal protective equipment is often debated is because it does have only limited utility. It has to be used appropriately. It has to be used properly. Workers, if you're talking about workers wearing personal protective equipment, or again, going back to my example of my chainsaw, if I'm out in a forest, if I'm cutting up firewood, I need to make sure that I've got my personal protective equipment with me, that it fits, that it's appropriately sized for my face, my facial features, or if I've got, earplugs, that those are appropriately designed. So personal protective equipment, again, necessary, but in and of itself is not as effective as means to design out that hazard entirely. Now, I told you I would give you an example. My most deadly, dangerous task that I face on a daily basis, I have to say, is driving to and from work. I drive a Toyota Corolla. I've driven a Toyota Corolla for the last 30 years. Not the same one, but I drive a Corolla to and from work. It's the biggest danger that I face. I drive about 15 miles. I spend about 25 minutes on the highway. About half of it is like full speed, 55 miles per hour, and the rest of it is between 40 and 25 miles per hour. It's still the biggest danger that I face daily. Is it possible for me as an individual, is it possible for me to design out that hazard entirely? Well, probably so. I mean, there are ways I could say, I'm not going to drive to and from work. I'm going to eliminate or significantly reduce my exposure on the highway. It's possible now for me to probably totally eliminate it. Well, maybe not totally. So because it's impractical sometimes to totally eliminate hazards, we then go to that second level of the safety hierarchy. But before I do that, I'm just going to say this. Have we already thought about this kind of thing to some extent? My biggest risk is probably either a combination of inattentive driving, or because I travel on Highway 14 at 55 miles per hour, I'm approaching oncoming traffic on a 2-lane highway at 55 miles per hour. Is it possible, if that's my biggest hazard, is it possible to design out that hazard? Well, that's exactly why we have interstate highways. We have interstate highways to fully eliminate, not fully, because we have the potential for people going the wrong way on a one-way, 4-lane interstate highway, but that has actually been a perfect example of the application of the safety hierarchy. We get people away from, we separate them in geographic space so that you don't have that risk or as great of a risk for a head-on collision. And what's the other thing that we've done with interstate highways? Head-on collisions are a big deal, but also the risk for a collision at an intersection. And so with interstate highways, we don't have people crossing interstates, right? We have exit and entry ramps onto the highway. And a big part of that is we have redesigned public highways, large interstate highways, that carry a lot of traffic consistent with the safety hierarchy. Number 2 on the safety hierarchy is safeguarding devices. So on my car, I've got a boatload of these. I have crash-resistant bumpers. I have airbags. I have seat belts and shoulder harnesses. I have a collapsible steering wheel. I have a windshield that has been designed in such a way that if there is a collision, I'm not going to have glass shattering into my face in most cases. So our public highways and our transportation system is full of safeguarding devices. Why? Because it's impractical to say, hey, no more driving, no more public highway travel. We're not going to build any more roadways. We're not going to build any more cars. Instead, what we're going to do is we're going to employ safeguarding devices. And guess what? We're not only employing safeguarding devices in the car, but we're also putting them on the highways. We've got rails. When I travel to and from work, I go around a couple of areas where there are fairly dramatic curves on Highway 14. There's also areas when I travel on Highway P here near Madison where I have very large steep drop-offs. So I have guardrails, all kinds of examples of public highway safeguarding devices, but also safeguarding devices in the vehicle itself. Warnings, I've already talked about this. Warnings, important, critical. My car, I look at my operator's manual in my Corolla, and I did check this out. I've got about 10 pages in those intro sections on warnings. I don't pick that operator's manual up and look at it on a daily basis. So those warnings are dependent on me reading them, remembering them, being able to recall them at the correct time, taking the appropriate protective action. And obviously, if we're talking about a hazard like a head-on collision, they're not going to be very helpful in terms of some of the things that are the most obvious and potentially the most deadly. So they're required, they're necessary, but by themselves, they are not adequate. The same with training. As a young driver, when I was 15 and a half years old, like a lot of you, I took driver's education. I actually used to be a defensive driving instructor with the National Safety Council, and I actually loved doing that back in the day. Training is really important, but you also need to be thinking about those higher levels. You need to be driving. You can be the safest driver in the world, but if you're driving in an unsafe vehicle or on an unsafe highway, you're going to have eventually a catastrophic failure of the system. And then last but not least, applying the safety hierarchy to me as a driver using personal protective equipment. It does seem a little bit silly. But guess what? If I'm on a motorcycle, or a couple of years ago, I just sold a moped. I dared not be on the public highways with my moped, which I occasionally was, without a helmet. So personal protective equipment does have its place. But in terms of being the most effective part of the safety hierarchy, it's not. So hopefully that gives you kind of a broad perspective on the safety hierarchy with the very specific example of automobile, motor vehicle, collisions, avoidance, application of the safety hierarchy. You might notice I just subtly changed that slide. What I would like for you to do, if you are a member of this class, is to apply the safety hierarchy per one of the discussion assignments that you'll find on Canvas. And I typically do this every year. I try to apply it. I try to ask students to apply it to something that's currently in the news. I've done a number of different airplane accidents or airplane disasters, actually, from recent incidents that have been in the news in the last few years. We also, a couple of years, did a little bit of analysis looking at things like self-driving cars and self-driving features. So there are lots of applications. And then eventually, in your homework assignment for BSE 508, I will have you apply the safety hierarchy to your project, along with the failure modes and effects analysis, because the two do sort of go hand in hand. And again, FMEA, failure modes and effects analysis, and other risk assessment methods are going to be referred to in video number 2. I encourage you to have a look at that. Hopefully this has been helpful for you, and I do look forward, for those of you who are in my class, to seeing how you're applying these principles to your design. For anybody else who's out there as an engineer, if you're watching this, if you'd like more information, feel free to get in touch with me, and I look forward to hearing from you soon.